Hello everyone, and welcome to this video short where we are going to reveal the unspoken truth about Python lists. Drum roll please. They are in fact implemented as dynamic arrays. So in this example, we're going to, in a sense, peek underneath the hood and see what some of these built-in structures in Python really are when it comes to their memory management and usability. This is important because it'll help us to better understand not only some of the lower level details, such as how these structures are being embedded and allocated in memory, but we can then determine how this is going to affect time complexity and runtime. So in this example, first import a number of tools to help us out with our analysis. And we're going to determine how and to what degree the lists are being stored in memory using some system tools. So first we get the size of the empty list here from our system, and then assuming that we are running with 8-byte buckets within our lists, we can determine the size of the list using this line of code here. And what we're going to do in these examples is start with an empty list and then repeatedly add items. And of course, when the list reaches its capacity, something's going to have to happen. And what happens is it's going to dynamically resize, that it's going to increase in size to allow for the addition of the new item. Of course, given what we know about dynamic arrays, this means that the system is going to reallocate a new chunk of memory for a new and larger list, copy all of the items from the previous list into this new list, and then start adding items into the new list. Again, all of this is done behind the scenes, and all of this extra copying will affect time complexity and runtime. So it's important to know this, which is why if you know the capacity of your list or the maximum capacity of the list that you're going to be using, it's a good idea to allocate it all at once rather than allowing for that dynamic resizing, because all of those extra copies will take time. All right, so here we run a simple example where we just look at the resizing nature of of the list. And so we can see here on the y-axis, we have the capacity of the list, and that is how many chunks of memory are being allocated to the list. And then on the x-axis, we have the number of appends and the number of items we've added to the list. So you can see here we start off with just one list, or the empty list, excuse me, and we have 0 buckets associated with it. As soon as we want to add an item, note that the capacity, that is the number of buckets allocated in memory, jumps to 4. So it looks like it's going to initially then start with a list of size 4, right? And then it stays at size 4 until we want to append something when it gets full here at size 4, in which case it jumps to a size of 8. It looks like it doubles in size. Right? And then, of course, when we try to add something, when we reach a number of appends of 8, right, it doubles in capacity again, indicating that we've resized dynamically. Right? Some of those extra copies have taken place and will have implications in the runtime. Right? So it looks like we have something on the order of an exponential resizing scheme, maybe on the order of 2 or somewhere around there. Again, why do we care? Well, this is important because all of that extra copying that's going to be done associated with the dynamic resizing is going to impact our runtime and slow down our code. Right? And to test this out, I've defined 2 little chunks of code here, 2 methods, to help with the timing and the different resizing schemes. So here we compute the time associated with dynamic resizing, and in this method we compute the time for statically allocating a list before doing the additions. Right, so in this example with the dynamic resizing, we start with an empty list and then just repeatedly add to the list. In this example, we pre-allocate, that is, we create a list of size n to start off, and then we do the n additions or n appendings. Right. In our last method here, we test out each and record the time associated with each. Right, so we run this when we have a number of appends, or in the number of assertions, we'll start with 2, right, and then we increase it by 100 and run multiple trials and identify how long it takes to run to complete those insertions or appends. And so given the resizing scheme and the nature of those unnecessary copies, it seems that, or we should observe that the dynamic resizing is going to be slower. That is, it's going to take more time as compared to statically allocating and reserving those memory locations and keeping the size of the array fixed and then just simply adding to them. Right. We plot the results, and after running some trials here, again, we're getting a little bit of variance here given some system features and the overall size of the runtime. Right? We can see here that, of course, both we have approximately linear increase or linear scale with respect to the size of the number of additions. And this is true. Whether we have dynamically allocated, this makes sense. And it makes sense if we have a resizing scheme for a dynamic array that is exponential, which we seemingly do. And these results corroborate that. What this also corroborates is that the static allocation, or simply reserving the memory, the total number of memory buckets needed to perform those maximum number of insertions, when that's done initially, we have a faster algorithm. Whereas if we use the dynamic resizing, right, we get a slightly increased runtime. All right. Well, thank you for joining me in this video short, and I will see you in the next episode.